3.4, concavity and the second derivative test, day 2. Now, if a function is increasing, two graphical representations are possible. Let's see. We have two coordinate planes. Draw some random graph. Well, we could have a graph that's increasing from left to right, looking like this. Or we could have a graph that's increasing left to right, looking like this. Okay, a couple things that are happening here. Okay, we know a function is increasing if f prime is greater than 0. That means we have positive tangent line slopes. But interesting enough, on this first graph, those tangent lines are underneath the graph, underneath the curve. On the second graph, we know these tangent lines are above the curve. So on and so forth. Okay, you can tell they look different too. For the first graph, we say that this graph, this function, is concave up. If you think about it, we have our tangent line has a slope of, say, maybe a small positive value. Then as you go along this curve, the tangent line gets steeper, therefore the derivative is increasing. Over here on the second graph, we have a pretty steep tangent line. Then as we go along, the tangent line flattens out. We know this, we call this, I should say, concave down. And we know f prime is decreasing on this interval. Okay, concave up, tangent lines are below, and they say concave up like a cup, because if you poured water in here, it'd hold water. F prime is increasing. Concave down like a frown, they say, and the derivative is decreasing. The derivative is positive in both cases, but in one case, the derivative is increasing, and one of them is decreasing. Likewise, we have two different graphical representations for a function that is decreasing. We could have a function that's decreasing left to right, like this. Or we could have a function decreasing left to right, like this. And in both cases, f prime is less than 0. We have a decreasing function. In one case, our tangent lines are below the curve. Okay, you can clearly see that. Since the tangent lines are below the curve and our actual value of the derivative is increasing. So here we have a negative, then a smaller negative, then a smaller negative number. We can say that our function is concave up on this interval. And our derivative is increasing. On the one on the right, our tangent lines are above the curve, and our values of the derivative are decreasing. They're getting smaller. Here's a smaller negative number, then a bigger negative number, and a bigger negative number. So our function is concave down. And f prime of x is decreasing. Definition of concavity: let f be differentiable on an open interval I. The graph of f is concave up on that interval I if f prime is increasing on the interval and concave down on the interval I if f prime is decreasing. And make sure when you're watching this, you can pause to write down the definitions and such. All right, concave up. Okay, we know f prime of x is increasing. What would that say about f double prime? Okay, think about it. If f is increasing, what would f prime be? Yeah, greater than 0. So if f prime is increasing, that means f double prime is greater than 0. For concave down, we know f prime is decreasing. The derivative values are getting smaller or more negative. Consider also. That means that f double prime is less than 0. Okay. Draw a random graph. You can see here, tangent lines are on top. Tangent line values, the slope values are getting smaller. We have concave down. And then it looks like we switch at about right here, we switch to concave up. Tangent lines switch from being on top to being underneath. I wonder what this point is called. We probably have some name for it. Test for concavity. Let f be a function whose second derivative exists. That's important. The second derivative has to exist on an open interval I. By saying the second derivative has to exist means the function must also be continuous on that open interval I. If f double prime is greater than 0 for all x on that interval I, then the graph of f is concave up like a cup on I. If f double prime is less than 0 on that interval, the graph is concave down. Again, make sure you pause the video if you need to and finish taking notes. Well, concavity can change. It can change at a point. We can change from concave up to concave down. All right, that point we talked about, that's called a point of inflection. A point of inflection, or POI, is an ordered pair where concavity changes. Point of inflection is where concavity changes. It is when the second derivative changes from positive to negative or from negative to positive. Points of inflection theorem. If C, f of C is a point of inflection of the graph of f, then either f double prime equals 0 or f is non-differentiable at x equals c. Why do we need this theorem? Because it tells us to find the points of inflection, we have to find when the second derivative is 0 or the second derivative does not exist. Those would be the places where a possible point of inflection could occur. Determine the points of inflection and discuss the concavity of the graph of f of x equals some convenient polynomial. Points of inflection, where do they occur? They occur when f double prime equals 0 or f double prime of x does not exist. That's where the possible points of inflection occur, but we have to have sign change for the second derivative. Well, let's find f prime. Now let's find f double prime. Now this is a polynomial, so the polynomial is continuous everywhere, and it exists everywhere, so we don't need to see or find when the second derivative does not exist. We'll set the second derivative equal to 0. And we'll factor if it factors. And it looks like we get possible points of inflection, x equals 0, x equals 2. Okay, these are possible points of inflection. Now, to see if they are actual points of inflection, we need to check to see if the second derivative changes signs. So just like we did for increasing, decreasing, local max, local min, we're going to set up a number line. Put our possible points of inflection, 0, 2, and we're going to check the second derivative now on these intervals. All right, the second derivative from negative infinity to 0. I'll pick -1 maybe. We get a negative value. We get a negative value. Negative times negative is positive. Check this other interval. Probably 1. We get a positive. We get a negative. Therefore a negative. And then check 3. Positive, positive, positive. Let's interpret what's happening. The second derivative is positive. That means the function is concave up. The second derivative is negative. That means the function is concave down. Second derivative is positive. Therefore, the function is concave up. And we do have sign change around these possible points of inflection. Therefore, 0 and 2 are points of inflection. Okay, points of inflection. X equals 0 and x equals 2 because f double prime x equals 0 and f double prime x changes signs. Okay, discuss the concavity of the graph. F is concave down on the interval 0 to 2 because f double prime of x is less than 0. F of x is concave up, negative infinity to 0, and 2 to infinity because f double prime of x greater than 0. Okay, up here, this point of inflection, f double prime change signs. Well, also, concavity changes. So these are all the steps we'd go through if we were given a function. We'd find the first derivative, find the second derivative, set the second derivative equal to 0, or find out when the second derivative does not exist. Those will give us our possible points of inflection. Test those points, those intervals that are broken up by those possible points of inflection, and interpret what's happening. All right, what if we're given a table now, though? So given the values for x, f of x, f prime x, and f double prime, answer each of the following. All All right, here's x, some random x values. Here's f of x, that means the height of the function. Here's f prime, which means the slope of the tangent line for the given x value. And we have f double prime for some x value. Now we got to use this table to answer some questions. All right? Identify all x values where f has a relative minimum. Okay, we're looking for critical numbers then. What does that mean? Where does f prime equal 0 or f prime dne and f prime changes? Okay, relative minimum, you're going negative to positive. All right, f prime, here's f prime equaling 0. But around that 0, we have positive changes to negative. That's not a minimum. Okay, here's where f prime equals 0. We have negative changing to positive. There we go. At x equals 3, we have a relative minimum. Don't just stop there. Go check the other stuff. All right, f prime is undefined right here, but f prime is positive to positive. Therefore, no relative max or min. Okay? Also, remember our second derivative test? If f prime equals 0, you can check the sign of f double prime. If f double prime is negative, that means concave down. That means we have a maximum. F prime is 0. F double prime is positive. That means concave up like a cup. That means you have a minimum. Okay? Okay, justify. Let's say relative min at x equals 3 because f prime x equals 0 and f prime x changes from negative to positive. All right, you could also say f prime x equals 0 and f double prime 3 is greater than 0. That would be okay also. Identify all x values where f has a relative maximum. Okay, similarly up above, we're looking for critical numbers, but we're looking for when f prime changes positive to negative. F prime equals 0 changes from positive to negative. We already excluded this one, this critical number, because f prime changes positive to positive, or it does not change. It stays positive to positive. Okay, relative max at x equals, gotta go check again, negative 1, because f prime x equals 0. Or you could also say x equals negative 1 is a critical number, and f prime x changes from positive to negative. Okay, not too bad. Identify all x values where f has a point of inflection. Justify. All right, point of inflection. Remember, f double prime of x equals 0, or f double prime x does not exist, and we have to have sign change. Okay, f double prime equals 0. Well, here's f double prime equals 0. That's a possible point of inflection. What do we got? Negative here, positive here. There we go. That would be x equals 1. POI at x equals 1 because f double prime x equals 0 and f double prime changes signs. Doesn't matter if it changes negative positive or positive negative, as long as we have change in the second derivative, which means concavity changes, then we have a point of inflection. Now what about this one? Yeah, I'm not too much of a fan of this one because the first derivative is undefined and the second derivative is undefined, so this actually should be undefined probably. But it does equal 0 in this chart, and it has positive to positive. Concavity does not change, therefore it's not a point of inflection. If they wanted the point, the actual point, we could say at x equals 1, y is negative 1, so we could say 1, negative 1. But of course, they said x values here. What is the equation of the tangent line at x equals 5? Well, to write the equation, we need an x and a y, and we need slope. What gives us slope? Derivative. Derivative when? When x equals 5. So we need f prime 5, and then we need 5, and whatever f of 5 is. Okay, what's f prime 5? Here's 5. F prime is 2. And then we'll have the point 5. Whatever f of 5 is, f of 5 is 3. And so very quickly we have y minus 3 equals 2 times x minus 5. And we are done.